The development of space-based navigation systems commenced in the 1950s with the establishment of the USA Transit System. The current generation began development in the 1970s, and the next generation is already under development. It's intended that Global Navigation Satellite Systems, or GNSS, will eventually replace all terrestrial radio navigation facilities. However, despite the United States' assertions that this is imminent, it's unlikely to be achieved in the foreseeable future. The current systems have brought a new dimension of accuracy to navigation systems, with a precision measured in meters, and where special differential techniques are used, the potential is for accuracy substantially less than 1 meter. At present, there are 2 operational GNSS systems. In addition, enhancements of the existing systems are under development, as is a European system. These systems are the Navstar Global Positioning System, which is operated by the USA, the Global Orbiting Navigation Satellite System, operated by Russia. There are some doubts about the long-term viability of this system because of the economic situation in Russia. Local Area Differential Global Navigation Satellite System, which provides improved accuracy and integrity to aircraft making airfield approaches. Wide Area Differential Global Navigation Satellite System, of which the European Geostationary Navigation Overlay System, EGNOS, currently under development, is a European contribution to a global augmentation system providing integrity and improved accuracy. The European Galileo project, which is at present a feasibility study, but is intended to start becoming operational in 2008. The principal reason the Europeans are developing their own system is one of internal security, since access to the full GPS or GLONASS facilities is outside European control. It can be anticipated that other countries or regions may develop their own systems for the same reason. Johannes Kepler's 3 laws quantify the mathematics of planetary orbits which apply equally to the orbits of satellites. His first law states that a satellite's orbit describes an ellipse with the Earth at one of the foci. His second law states that a satellite sweeps out equal areas in equal time. And his third law states that the square of the satellite's orbital period is proportional to the cube of its average distance. Using these laws, and given a starting point, the satellites, or space vehicles as they are normally called, calculate their positions at all points in their orbits. A space vehicle's orbital position is known as ephemeris. When you switch on your GPS in your aircraft, the receiver knows from its internal clock and memory which space vehicles it can expect to see. It then constructs a 3-dimensional fix using information from 4 of these vehicles. The following diagrams will give you an idea of what is involved in this process. Each range corresponds to a position somewhere on the surface of a sphere, with a radius in excess of 10,900 nautical miles, as shown here. However, we could be anywhere on the circumference of the sphere. We can slightly improve the situation by using 2 range spheres to give a circular position line. The introduction of a third range sphere will produce 2 positions several thousand miles apart. One position will be on or close to the surface of the Earth. The other position will be out in space, so it would be possible to use just 3 spheres to produce a position by rejecting the space position. However, a 4th sphere is needed because of the way the receiver compensates for time errors. The details of this are outside the scope of this lesson. Suffice to say that the use of 4 space vehicles provides an accurate 3-dimensional fix, which can be readily transposed into latitude and longitude or any other Earth reference system. The GPS comprises 3 segments: the space segment, the control segment, and the user segment. GPS time is measured in weeks and seconds from 000000 UTC on the 22nd of August 1999. The time restarts at 0 after an epoch, which is 19.7 years, or 1024 weeks. GPS time is referenced to UTC, but does not run in direct synchronization, so time correlation information is included in the space vehicle broadcast. The accuracy of GPS is of the order of 5 meters. However, it has a variety of errors, most of which are compensated for within the system. Ephemeris errors are errors in the space vehicle's calculation of position caused by the gravitational effects of the Sun, Moon, and planets, and solar radiation. The vehicle's position is checked every 12 hours, and where necessary, updated. As with ephemeris, the space vehicle clock is checked at least every 12 hours, and any error passed to the vehicle. The ionosphere affects radio waves of all frequencies, the actual effect being dependent on the frequency. The space vehicle broadcast contains a model of the ionosphere which is used to make time corrections to the measured time interval. The state of the ionosphere is continuously checked at the monitoring stations, and the model is updated to the space vehicle at least every 12 hours. This is the most significant of the errors in space vehicle navigation systems. If two different frequencies are available, then the space vehicle can deduce the ionospheric effect on the transit of the signals and make appropriate adjustments to the observed times, thereby minimizing the error. Because of the inherent accuracy of space vehicle navigation systems, the effect of variations in tropospheric conditions on the passage of radio waves has become significant. Variations in pressure, temperature, density, and humidity affect the speed of propagation. For example, a change in transit time of 1 nanosecond gives an error of 0.3 of a meter. As with ionospheric propagation error, this is minimized with the use of two frequencies. All radio receivers generate internal noise, which can cause errors in the measurement of the time difference. Reflections from the ground and parts of the aircraft result in multipath reception. This can be minimized by careful sighting of the aerial and by internal processing techniques. Geometric dilution of precision is the term for a poor cut between position lines. GDOP occurs when the space vehicles are relatively close to each other. Errors caused by GDOP are minimized by the geometry of the positioning of the space vehicles in their orbits, and by the receivers selecting the 4 best space vehicles to determine position. The space vehicle geometry that will provide the most accurate fixing information is one space vehicle directly overhead the receiver, and the other 3 space vehicles close to the horizon and spaced 120 degrees apart. Aircraft maneuvers may result in part of the aircraft shadowing one or more of the in-use space vehicles. There are 2 possible outcomes of this. Firstly, whilst the space vehicle is shadowed, the signal may be lost, resulting in degradation of accuracy, or the receiver may lock on to reflections from other parts of the aircraft, again with a reduction in accuracy. The effect of maneuvers can be minimized by careful positioning of the aerial on the aircraft.